Thanks for joining me. We're about to go through and do some practice problems. Now, you know we've heavily invested in this. In particular, if you look somewhere down here, you'll discover there's a pause button. That's an amazing feature of this video. You see, what you can do is once you see a problem, pause. Think about how to do it. Better yet, do the whole problem. And then, once you're ready, unpause. And even if you can only do part of it, do as much as you can. The more you can do by yourself, the better you'll get. All right, let's begin.
Suppose that f of xy has second-order Taylor polynomial. G of xy is 5 minus 2x plus 6y plus 3x squared minus 2xy plus 7y squared at 0, 0. Find the values of f sub x 0, 0, fxx 0, 0, fxy 0, 0. All right. So you might say, wait, is that a typo? Is that supposed to be an f there? No, no, no. It's supposed to be a g. G is an approximation to f. Namely, we would call it the quadratic approximation, but in this case, we're calling it the second-order Taylor polynomial. You know, you say potato, I say potato. Same idea. Now there's some good news here. Notice that this is the approximation at 0, 0. Every time we talk about an approximation, it's an approximation at a particular location. And this makes this problem really quite easy. They didn't do any expanding it like, oh, you fool, why did you expand? We'll see one like that later on. But okay, so how do we proceed? Well, this problem really comes down to reading off the coefficients. So we need to understand what the coefficients are. So let's do this in sort of a little bit slower than we might normally do it. But we'll say, look, g of xy, because we know it's the second-order Taylor polynomial at 0, 0, if we were to write it out symbolically, and it would be f at 0, 0 plus fx at 0, 0 times x minus 0 plus fy at 0, 0 times y minus 0 plus 1/2 fxx at 0, 0 x minus 0 squared plus fxy at 0, 0 x minus 0 y minus 0 plus 1/2 fyy at 0, 0 y minus 0 squared. You can see these problems take space. There's a lot to write down. Now that's what it is if we just say second-order Taylor polynomial at 0, 0. Now let's write down what we actually have. We have 5 minus 2x plus 6y plus 3x squared minus 2xy plus 7y squared. And now it's the great, we're matching things, right? So we just start reading off. What is it we want to find? Well, we want to find things such as f sub x. So we say, okay, well, here's an f sub x. So that's got to match. And we want f sub xx. Okay, here's an f sub xx. That's got to match. And we want f of xy. And then that's got to match. So in particular, fx at 0, 0 is negative 2. Now for fxx, remember there's this factor of a half, so don't forget that. So a half fxx at 0, 0 is 3. So fxx at 0, 0, 3 times 2 makes 6. And fxy at 0, 0 is, again, negative 2. And we're done. So this problem tests us on, do we know what the second-order Taylor polynomial is? Can we read off the coefficients? And probably the biggest place where people might trip, assuming they know, of course, the form, is the halves. So the halves go with the fxx and fyy. Does not go with the fxy. So don't forget that part. All right, but otherwise, nice start, nice and easy. Let's keep that spirit going the whole way through. use Taylor's formula to find the quadratic approximation of sine of 2x e to the 3y near the point pi 0. Okay, so Taylor's formula just says the formula for quadratic approximations. And so in particular, let's suppose we think of this as our f of xy. Then, for a quadratic approximation, that means we're going to go up through second order derivatives. We have that f of xy is approximately, we'll have f at 0, let's pay attention here, pi 0. You gotta remember where you're centered at. So many times we do it around 0, 0, but not this time, so we gotta pay attention to that. So let me correct that. So it would be, we're gonna plug in f of pi comma 0 plus f pi 0, f sub x pi 0, x minus pi, plus f sub y pi 0, y minus 0. All right, that's the 0th order derivative. The first order derivatives. Now we get into the second order derivatives. So I'll go to the next line because I'm going to run out of space anyways. Plus 1/2 fxx pi 0, x minus pi squared, plus fxy pi 0, x minus pi, y minus 0, plus 1/2 fyy of pi 0, y minus 0 squared. All right, so we're basically plugging into that. Now, this is not the answer because we've got to find these numbers here. So, to do that, we need to take derivatives. So the problems aren't particularly bad. It's just going to be lots of derivatives, lots of writing. And so you got to pace yourself. Say, look, I know what I need. I need to take the function, all the first derivatives, all the second derivatives, and then evaluate, and then plug it in, and then catch your breath, check to see if you've reached the end, and hopefully life is going great, right? Well, so let's begin. All right, well, we'll start at the very beginning. That's a very good place to start. So we have our sine 2x e to the 3y. So f sub x of xy. Well, taking the derivative with respect to x. Derivative of sine, cosine. So it'll be 2 cosine 2x, and the e to the 3y comes along like it were a constant. 2 from the chain rule. F sub y, xy, that now the sine 2x is like a constant. The 3 comes down. 3 sine 2x e to the 3y. fxx. All right. So taking the derivative here with respect to x again, derivative of cosine, negative sine. Don't forget to bring the 2 out. So negative 4 sine 2x e to the 3y. fxy, xy, whoops, fxx, I forgot to put the 2 x's there. Now, for fxy, I can come and take the derivative with respect to y of f sub x, or the derivative with respect to x of f sub y. Oftentimes, it's about the same work, and it looks like that's the case here. So I'll start with f sub x and take the derivative with respect to y. What will happen? A 3 will come down. So this will become 6 cosine 2x e to the 3y. And fyy of xy, well, that'll become 9 sine of 2x e to the 3y. Okay, so once we've taken our derivatives, now we need to evaluate, because these aren't functions, these are numbers. So don't forget to evaluate. So we're plugging in pi and 0. So f of pi 0, well, sine of 2 pi is 0. So that's going to make it nice. All right, how about f sub x at pi 0? Well, cosine of 2 pi is 1. E to the 0 is 1, so we have 2. F sub y at pi is 0. Well, sine of 2 pi is 0, so that's makes that one short work. Fxx at pi is 0. Well, again, we have sine of 2 pi, which is 0. Fxy at pi is 0. Well, cosine 2 pi is 1 times 6. E to 0 is 1, so that's 6. Fyy at 0. Sorry, fyy at pi comma 0. Sine of 2 pi is 0 again, so 0. So that's okay. Lots of zeros. We don't mind lots of zeros. So what are the pieces that aren't going to be zeroed out for us? Well, for us, we will have an fx term and the fxy term. Everything else is already 0. And so our answer will become 2 times x minus pi. And then we have our fxy, which is 6, x minus pi y. And that's our answer. That's the second order approximation, the quadratic approximation, if you will, of the function sine 2x e to the 3y near the point pi comma 0. All right. Find parametric equations for the normal line to the surface described by the equation sine of 2x minus yz squared plus e to the xy minus 2x plus 4y equals 7 at the point 0, 2, 1. Okay, all right. So let's think about what we're doing. So we're looking for a line. That's good. And we're going to give it in parametric form. So parametric form for a line. All right. Now there's a key word here, and let's stare at it for a second. That key word is normal. All right, now let's think about that. Where have we seen normal? Normally, this is where I might give a hint, but I think we've seen normal before. So like normal vector. We've talked about normal vector. Those are the vectors which are perpendicular to the plane. So when we see this word normal, we should really say, oh, you know what? Normal is really a stand-in for perpendicular. Say, yeah, that's a good way to think of it. Okay, so if I think that the normal line should be perpendicular, it's like, okay, so it's like we're trying to find something that's perpendicular to the surface. All right. Now, with that in mind, it's going to make our search a fair bit easier. Okay, so what's going to happen? Well, right now we can think of this as an implicit surface because we don't have z as a function of x and y. Rather, we have this sort of crazy thing described where all the variables are kind of jumbled up together. And that's okay. We can handle this. And in particular, we're in a good situation. Now, what I mean by that is if you look at what you have sine 2x minus yz squared plus e to the xy minus 2x plus 4z equals 7. So all the variables are on one side, and on the other side is a number. Now, no variables over here. That's what you want. If there were a variable over here, what would you do? Move it to the other side. All right. So now we say, what can we do? Well, we're thinking this as a function of x, y, z. And this is the great insight. Thinking of it in that way, what we really have is a level surface. And, this is cool, gradients are perpendicular to level surfaces. So, our great aha is that the direction of this normal line, so, what's perpendicular, is going to be coming from the gradient to this plane. This gradient to the surface. So, the direction vector, we're just making notes here, is going to be equal to the gradient of f at the point 0, 2, 1. So our big next step is to take the gradient. And all right, great. Well, let's do that. Seems like a reasonable thing to do. So we have that the gradient of f, we'll not evaluate it yet, we'll just take it. So we'll go through, take the derivative with respect to x, derivative of sine, 2 cosine 2x. Let's see, no x there. Here there's an x, so we have a plus y e to the xy. There's an x there, so a minus 2, comma. Now take the derivative with respect to y. Nothing there. Minus z squared. Here there's going to be a plus x e to the xy. And that's it for the y's. Okay, comma. How about z's? There's no z there. There's a minus 2zy or minus 2yz. No z there. No z there. And a plus 4. All right. So now plug in. So gradient of f at 0, 2, 1. So everywhere where you see an x, put 0. Where you see a y, put a 2. Where you see a z, put a 1. Well, okay. So we have 2 cosine 0. Cosine 0 is 1. So that'll become 2. Plus 2 e to the 0. Well, e to the 0 is 1. And so, okay, that's going to become 2. And minus 2, comma. Minus z squared, which would be minus 1. And then there's an x, 0 times, well, what's it? 0 times something hard to recover. 0, comma. Minus 2 times z times y. So minus 2 times 1 is minus 4. And then plus 4. And say, okay, great. Which gives us what? It gives us 2 minus 1, 0. Now, is it okay that we have a 0? Yes, it's fine. What if they were all zeros? Uh-oh. Then we'd be in trouble. But we don't have all zeros here. Okay. So, yeah, we're doing great. What's left for us to do? How do we wrap up this lovely problem here? Well, remember, this is our direction vector. We've already got our point. So as a reminder, we say, look, here's our point. All right, point plus direction equals line. Since we haven't talked about lines in a little bit, let's just remind ourselves. So generically, we'll have x equals, y equals, z equals. And then we're going to have two slots. The first slot is our point. And then we're going to have plus, 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 something t, something t, something t. And this is our direction vector. So in our case, what do we write in? Well, our point is 0, 2, 1. And our direction vector is 2, -1, 0. And so we get our parametric equations are x equals 2t, y equals 2 minus t, and z equals 1. And there's our line. This line will intersect the surface in a perpendicular fashion, and we would call that the normal line. All right, we did it. Woohoo! Let's keep going. Find and classify the critical point AB of f of xy equals 4 log x plus y minus 4x plus y squared. All right, now we get to do two things. We get to find and we get to classify. So we always have to find first because we can't classify until we found something. All right, well, let's start with the find. How do we find critical points? Well, critical points or where our derivative is going to be undefined. This is not going to really be a problem for us in this class, so focus on the other issue, namely, where is the derivative 0? Of course, what do we mean by the derivative being 0? We really mean where is the gradient 0, or in other words, where is the tangent plane flat? All right, so we're going to do that by saying where are the partial derivatives 0? Okay, so idea. We're going to set 0 equal to f sub x. So we go through and take the derivative with respect to x. Say, well, with the derivative with respect to x, the first term, 4 over x plus y, minus 4, and nothing. Now I'll do the same thing, but f sub y. Okay, derivative here, 4 over x plus y. Okay, that goes away. Derivative of y squared, 2y. All right, so we now have two equations and two unknowns. Now, unfortunately, they're not quite the easiest two equations and two unknowns most of the time. But take a moment and just stare at them and say, huh. Or you could say, huh. Maybe you'll say, ah. You know, we'll have a roller coaster of emotions. So it's helpful to sit back and sort of say, can I do anything? Well, if you look at them and say, you know, they're very similar to each other. And actually, really, the parts where they differ are these little pieces here. 0 equals 4 over x plus y minus 4. 0 equals 4 over x plus y plus 2y. So the only way this can both work is if these little parts match. So that's our great aha. So we say, okay, so that says we need 2y to be negative 4, or, if you like, y is negative 2. Okay, now that's not a point, but that gets us part of our way. It's the y coordinate. Now how do we get the x coordinate? Well, now we plug in what we know and solve. So, all right, let's suppose we go to our first one. Say, let's plug in y is negative 2 into there. That would say 0 is equal to 4 over x minus 2 minus 4. Well, okay, you can move the 4 across. 4 equals 4 over x minus 2. Well, the only way this is possible is if x minus 2 were equal to 1. Right, you can cross multiply, also divide by 4. Well, that really says, hey, x is 3. So this is the y coordinate, here's the x coordinate. So our critical point is at the point 3 comma minus 2. All right. Now, that's step 1. We still have plenty of space because we have a step 2. Classify. Now, classification basically boils down to the second derivative test. So, that means we're going to have to take second derivatives. All right, here we go. We have f(x)(x). So taking the derivative of this with respect to x will give us a negative 4 over x plus y squared. And in case you're wondering, like, where is this coming from? You can think of it as a quotient rule. You can also think of it as saying, oh, 4 over x plus y is the same as 4 times x plus y to the minus 1. So we're going to take the derivative, the minus 1 comes down, that's where the minus comes from. X plus y to the minus 2, that's where the square comes from. And then times root of the inside is times 1. All right, the derivative of negative 4 goes away. All right, and by the way, this already tells us what it can't be. Can't be a mint, but that's another story. We'll get to that in a second. All right, how about f, x, y? Same thing, right? Negative 4 over x plus y squared. Because same derivative here, derivative of negative 4 is 0. What about f, y, y? Well, again, negative 4 over x plus y quantity squared. And then derivative of 2y plus 2. Okay, Now, the next thing we have to do is for each one of these second derivatives, we need to evaluate. And we're going to evaluate at each critical point. Well, there's only one. So that's good news for us. And really great news for us is that the way we evaluate is we really have x plus y. And we already know what x plus y is, well, because we can do it. X plus y is 1. So fxx at 3, negative 2 will be negative 4 over 1 squared. So that's negative 4. fxy at 3, negative 2 is negative 4 over 1 squared. fyy at 3, negative 2 is negative 4 over 1 squared plus 2, which is negative 2. Okay, so we now are ready to finish our second derivative test. We've computed our pieces. So here we go. Let's recap what the second derivative test tells us. So the second derivative test says do the following. We're going to compute this discriminant. We ran out of symbols, so d for discriminant, even though d often is used for determinant. And, d is also derivative. D is used for so many things. Okay, so we take our fxx at our critical point, I'll call it p, times fyy at our critical point times p, subtract fxy at our critical point, p squared. Now, a couple possibilities. If this is positive, then you further break and say if xxx is negative, then this is a max. If xxx is positive, this is a min. Now, the reason I said we already know it can't be a min is I saw that fxx was negative. So that ruled out min. If this is less than 0, then you get a saddle. And if this is equal to 0, we have no idea. Okay, so that's the test. What do we have for ourselves? Well, for us, we have negative 4 times negative 4, subtract, not times negative 4, negative 2. I misread. So fxx, fyy, negative 4 times negative 2, subtract negative 4 squared. So this is 8, subtract 16, which is negative 8. The value doesn't matter, the sign matters. That's less than 0. So that tells us that we are in a saddle. Okay, so critical point at 3, negative 2, and it is a saddle. That's the classification. All right, there we go. Woohoo! Find and classify the critical points of the function g of xy is x cubed plus 12xy plus 8y cubed. All right, again, find and classify. So there's 2 steps. Find, classify. So let's begin with find, because we have to. You can't classify it until you found it. So, all right, so we're going to find it, and that tells us we're setting the gradient of our function equal to 0. And so in particular, we're going to get 2 equations, 2 unknowns. So we're going to get really good at this 2 equations, 2 unknowns. So 0 equals g sub x equals 3x squared plus 12y. And we also have 0 is g sub y. Well, that's 12x plus 24y squared. All right. So now we have to solve. But there's a challenge. The challenge is these aren't linear, right? It's not like x and y. It's like x squared and y. And here's x and y squared. And so it's like, okay, well, got to be more careful. But that's all right. We're good at being careful. We never rush into anything, I hope. So let's think about what we can say. One thing we can say is, looking at this, let's suppose we come to this first equation here. This says I can move the 12y across. 3x squared equals negative 12y, or x squared is negative 4y. All right, that's divided by 3. I can move the 12x across, I guess. Yeah, let's move the 24y squared across. Make it sort of more fitting. 12x is negative 24y squared. Divide by 12. X equals minus 2y squared. All right, good, good. Now, what can we do? Well, this is really nice. Notice that we solve for x here. So, idea. We've talked about elimination, but we can also talk about substitution. It says, hey, we could take this minus 2y squared and plug it in for x in the other equation. Ah, I like where we're going with this. Okay, so if we do that, we have that negative 2y squared squared. So we're squaring the whole thing, right? We're substituting for x equals negative 4y. Now this is good news for us because we have one equation, one unknown. Our favorite kind of equation. Well, assuming we can solve it. Okay, so what does that say? Well, or that says 4y to the fourth equals minus 4y. Now you might be saying, oh, let's divide by y. No. No. No, 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 no. Don't do that. Why not? Well, you have to be careful. You don't want to divide because you might lose solutions. A way to think of it is you can't divide if what you're dividing by could ever be 0. Because if you were dividing by 0, essentially you were losing a solution. So if you can't divide, what can you do? Well, you can move across and factor out. Now, before we do that, we will divide by 4, and we're not going to have our like, no, 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 no. No, we're not going to have that conversation because 4 is 4. It's not 0. Okay, so divide out by the 4, move the y across. Okay, so that tells us that y to the fourth plus y equals 0. Okay, so y times y cubed plus 1 equals 0. Now, two possibilities. One possibility is y equals 0. The other possibility is that y cubed plus 1 equals 0. Well, okay, if y equals 0, then y equals 0. And remember, x is minus 2y squared. So if y equals 0, x equals 0. All right, no worries. Here, this says y cubed is negative 1. Take the cubed root. You don't have to worry about plus or minus with the cubed roots. The cubed root of negative 1 is negative 1. So y equals negative 1. Now x is negative 2 times negative 1 squared. Well, that tells us that x is negative 2. Okay, so let's recap where we're at right now. So we have our critical points, and there's 2 of them. Okay, yeah, you can have multiple critical points. You can have a lot of critical points, but here we have 2. So we have one at 0, 0, and one at negative 2, negative 1. All right, good, good, good. So, 2 critical points. Our find is done. But our journey's not. We have to do our classify. Ah, wonderful. Just when we thought this problem was over, it pulls us back in. Ah, this is great. Okay, so we start doing our second derivative test, our second partials test, if you will. So we need our second derivatives. Well, we have our first derivatives. So what about gxx? Well, that'll be 6x. Gxy? Well, that'll be 12. Gyy? Well, that will be 48y. Wow, that's a big number, but that's all right. Big numbers don't frighten us. Okay, so we have our discriminant. All right, so so d, that's gxx, gyy minus gxy squared. So that's going to be 6x times 48y subtract 12 squared. And 6 times 48, it's a big number. We're amongst friends. Do we really need to know that number? Yeah, let's just call it 288. It turns out it is 288, but in some sense, we don't really care the exact value. We just need to know enough to make decisions. Okay, now, the moment of truth. We plug in. We plugged in 0, 0. So let's do that. And we're going to see what happens. So at 0, 0, we get that the discriminant at 0, 0 is 0 subtract 144, which is negative. If you get a negative number out, what that's telling you is in one direction you're going down, but in a different direction you're going up. So if you're going down here, but you're going up here, saddle. Okay, saddle. All right. Well, great. So 0, 0, saddle. Now, what about at -2, -1? Okay, so we plug that in. We're going to get 288 times -2 times -1, subtract 144. Now, do we want to do this computation? Do we need to do this computation? We actually don't have to get the exact number. We don't have to know that 288 times 2 is 576. We don't care. That's 576. What we really care about is we say, is this going to be positive or negative? Well, this is a large positive number. It's a lot bigger than 144. So we can see it's positive. And so we're like, ooh, K, positive. That tells us it's a min or a max. It doesn't tell us which. It tells us that we're always either going up in all directions, so we're either always going up or either always going down. How do we know? Well, now we go to a slice. In other words, we look at either gxx or we look at gy. It doesn't matter, pick one. We say, well, gxx at -2, -1 is -12, which is less than 0. That tells us we're going down. Maximum. And another way to think about that, or another way to remember that, is it's truly the second derivative test for single variable calculus. And the way I remember the second derivative test, if your second derivative is negative, you look like that. And so you notice in particular you have a max. If your second derivative is positive, you look something like that. And so you're at a min. And if your second derivative is 0, oh, you have no idea what's going on. So, but good news, we do know our second derivative here is negative. It is a max. And so that finishes to classify, and so we finish the problem. We have found, and we have classified. Life is wonderful. Good. Good. A cone with height h and radius r has a lateral surface area of, and there's a formula. Surface area is pi r squared root r squared plus h squared. Using a linearization, which is also called a first order Taylor approximation, which is also called a tangent plane. Okay, it's called lots of things. At the point RH equals 6, 8, estimate the change in the surface area when r decreases from 6 to 5.95 and h increases from 8 to 8.1. All right. Now let's talk about what's going on, and let's just mention a few things. You might wonder, what does this mean? Lateral surface area. Well, first off, it's a cone. And so you say, okay, so imagine you have a cone. And so here's a cone. So the lateral surface area, for lack of a better phrase, it's just the surface area on the side. So here's our cone, and there's some sort of surface area that we have going on. So, all right. So it's our surface area. If you were thinking of this as like a wizard's cap, for example, and so it's not a solid cone, but just the fabric there. That's the lateral surface area is how much material do you need to make it. Now, in terms of our diagram here, we don't need to know this, but it's nice to know things. So we'll go ahead and mark h is the height, then r here is the radius. Okay, all right, so what do we have? Well, we need to think of this as a function, and we say, all right, we're after a change in the surface area. Now, before we go through and actually do the computations, let's just remind ourselves first order Taylor approximations, linearization, tangent plane, whatever you want to call it. If we're thinking of this as a function, it says, the surface area at r and h is approximately the surface area at the initial point. So this says 6, 8, plus the surface area, take the derivative of that with respect to r, at 6, 8 times r minus 6. So change in r, we'll get back to that. And plus surface area derivative with respect to h at 6, 8, h minus 8. So this right here is our first order Taylor approximation. Now there's an important phrase here, and I want to make sure we understand what we're being asked to find, because if we understand that, it will change the way we approach this problem. We are asked to estimate the change in the surface area. So we're not being asked to say, hey, what's the new surface area? We're being asked to estimate the change in the surface area. So we're not after figuring this out. What are we after? Well, what we're after is the current surface area minus what we had before. So in fact, what we would do is we'd say, okay, this surface area, subtract the current surface area. This is our change in our surface area. Okay, so that would be approximately this derivative of, with respect to r of our surface area, times change in r, and plus derivative with respect to h of our surface area, change in h. So, plan. We need these derivatives. Now, do we know change in r? Yes. What happened? Well, r went from 6 to 5.95. So we could say, oh, change in r, it went down. This is negative 0.05. Or if you're a fan of fractions, and who isn't a fan of fractions? I'm not. This is the same as negative 1 over 20. On the other hand, change in h, you went from 8 to 8.1. Okay, so that says you went up by 0.10 or 1/10. All right, good. So, what do we need? We need some derivatives. So what are we going to do? We're going to do some derivatives. Okay, all right. So let's start. We have that our surface area as a function of r and h is pi r times, and we're going to write this in our calculus-friendly way, the 1/2 power. So, taking the derivative with respect to r, R shows up in two places, so we're going to need to do a product rule and a chain rule. So the derivative of the first will just leave us with pi times 1. We have the second, r squared plus h squared to the 1/2, plus pi times r. Then the derivative here, the 1/2 comes down, r squared plus h squared to the minus 1/2, and then times rid of the inside, which will be 2r. Well, okay, the 2's cancel, and if we rewrite that a little bit more legibly, pi r squared plus h squared to the 1/2 plus pi r squared plus h squared to the minus 1/2. All right, good, good. Now, when we take the derivative with respect to h, it's a little bit easier because there's only one h. So you get the pi r, then you, again, 1/2 r squared plus h squared to the minus 1/2 times rid of the inside is 2h. So you get pi r h, and the 1/2s and the 2's cancel, and so you end up with r squared plus h squared to the minus 1/2. Okay, so now we need to evaluate. So we're very close to being done, very close. So let's see, where do we have space? I think we maybe have space over here. So SA sub r, the derivative of surface area with respect to r at 6, 8 is, well, let's work through some terms here. So 6 squared, 36, 8 squared, 64, 64 plus 36 is 100. Square root of 100 is 10. So that's 10 pi plus, we get pi r squared, which is 36, times, and this is, again, it's going to be 10, but the minus is a 1 over 10. 1 over 10. Okay. All right. Well, 36, well, I can divide by 18. Then I can think of 10 as 50 over 5. So this would be 50 over 5 plus 18 over 5 makes 68 over 5 pi. Okay, so that's SA sub r at our point. Okay, so that goes here. So this is 68 pi over 5. All right, we'll come back and revisit these pieces. Now, SAH at 6, 8. Here we go. We're going to get pi, and then we have times r times h, so times 6 times 8, so that's 48, and r squared plus h squared to the minus 1/2, well, that's really, again, 1 over 10, so times 1 over 10. Okay, so this part right here is 48 pi over 10. All right, now let's see what we have here. We have, both terms have a pi. I'm going to factor that out. And then here we have minus 68 over 100, right? Minus 68, 100. Here we have plus 48 over 100. Okay, that's looking very promising, by the way. So minus 68 plus 48 would give us what? It gives us minus 20. So this is pi times minus 20 over 100, or if you like, that's minus 1/5 pi. And there you go. So our surface area will decrease, and it'll go down by the amount of decrease is 1/5 pi. All right. Whew. Now, it's not so bad. Well, of course, you got to pay attention to a couple of things. We're after change, And so it just sort of says, okay, rate of change with respect to r, amount of change with respect to r, rate of change with respect to h, amount of change with respect to h. So you have to find your rates of change, evaluate. You have to find your amounts of change, and then you clean it up. And then life is good, wonderful, hurrah, huzzah, woohoo! Consider the surface S, defined by the equation x cubed plus 3x squared plus y squared minus 4y plus 6z is negative 7. Find all points p equals x, y, z, so that the vector v is 3, 2, 2 is normal to the tangent plane to S at P. All right. Now, who knows? Maybe all points is 0 points. Maybe it's many points. We'll have to figure that out. Okay, so a couple of things. Let's see what we're at. We don't have this as an expression of z. We could, but it's kind of telling us it wants us to go in a particular direction. We'll embrace the direction it's asking us to go. Namely, it says, hey, you know, you got this expression which involves x, y, z. You can think of it as a function of x, y, z equal to a constant. Oh. So if we're thinking of it in that way, then what we really have is that this surface is a level surface of some higher dimensional object. And because it's a level surface, we have our great aha, namely that we say, oh, do you know what's perpendicular to level surfaces? Gradients. And so we say, okay, the gradients make the normals. So, idea, this is a gradient problem. And it is. It's all about the gradient. So, we say, all right, well, let's figure out what our gradient turns out to be. So in our case, we have the gradient of f is, taking the derivative with respect to x, 3x squared plus 6x. Nothing else has an x in it. Taking the derivative with respect to y, 2y minus 4. Nothing else has a y in it. Taking the derivative with respect to z, 6. And nothing else has a z in it. Okay, so there's our gradient. Now, what are we going to do? Well, we need to say what's true. Well, our gradient has to be somehow normal to our tangent plane, which is true, but this is also normal to our tangent plane. Now, does that mean that this vector equals that vector? No. It means that that vector is a multiple. These two vectors are parallel. So that's an important idea. They're not the same vector, they're parallel. So this has to be some constant c times the vector 3, 2, 2. Now the question that's going to come up is what's the right value for c? And that's kind of what we've got to figure out. However, I don't think it's going to take us long to figure that out. Look at this third entry. Very conveniently, it's very uninteresting, which is useful. Being uninteresting can be very useful. That's why people like to talk to mathematicians. We're not very interesting, we're incredibly useful. So, why is it useful? Well, this third entry has to match with the third entry over here. Now you might say, well, wait, 6 and 2 don't match, but don't forget about that c. So it says, oh, you're right. This tells us that 6 equals 2 times c. So, what's the right multiple? 3. Aha. So, what we really say is that this has to be equal to 9, 6, 6. And so, the third entry is guaranteed to match. And so we now need to match the remaining entries. So we say, okay, well, that has to match. You know, the y entry has to match. And then the x entry has to match. Okay, so let's talk about what the consequences are. We can start with the y entry. We can say, look, we have that 2y minus 4 has to equal 6. So 2y has to equal 10. So y equals 5. All right. So we now know that for the points that we're after, they all have to have the form y equals 5. All right. What about the x coordinate? Well, let's look on that one. 3x squared plus 6x has to equal 9. Well, okay, so we can move that across. 3x squared plus 6x minus 9 has to be 0. All right, very 3 here. Divide by the 3. X squared plus 2x minus 3 has to equal 0. That looks like it has a chance to factor, because it can. All right, so how does it factor? Well, we need two things that add to 2 but multiply to negative 3. So for instance, it could be x plus 3, x minus 1. Does that work? X squared, good. Minus x plus 3x, yeah, plus 2x minus 3. So x equals negative 3 or 1. So we've now have a good handle on the y coordinate, and we have a good handle on the x coordinate. And in fact, we have two options for the x coordinate, but only one for the y. So at this point, right now, we can say we currently have the following. Namely, that we have a point where x equals 1, y equals 5, z equals something, and a point where x equals negative 3, where y equals positive 5, and z equals something. And so those are our answers. However, I put a box, but these answers are not complete. We gotta patch the hole. How do we get the z? Well, we go back to our original expression. Okay, so now we're going to plug in what we know and solve for what we don't. In this case, we know x and y. What we need to solve for is our z. So we're going to do this twice. So let's start with our first case. X equals 1 and y equals 5. All right, so here we go. 1 cubed plus 3 times 1 squared plus 5 squared, 25, minus 4 times 5, which is minus 20, plus this number 6z has to equal negative 7. Well, okay, so 25 minus 20 is 5, and then we have plus 3 is 8, plus 1 is 9. Okay, so that says 9 plus 6z is negative 7. Okay, so we can subtract 9. All right, so, or 6z is minus 16. Or z is minus 16 over 6. And, well, we can divide by 2. You get minus 8 over 3. So, our coordinate is 1, 5, minus 8 over 3. All right. We probably wouldn't have guessed that coordinate. So, what about the other one? Whew. Well, let's do it. So we have that x equals negative 3, y equals 5. So again, we're just going to start working our way through. Negative 3 cubed, negative 27. Right? Negative 3 times negative 3 is positive 9. Positive 9 times negative 3 is negative 27. 3 times negative 3 squared, that's 3 times 9, that's plus 27. 5 squared, plus 25. 4 times 5 is 20, so we're going to subtract 20. And then we're going to add 6z, and that's going to be negative 7. Well, the 27's cancel, that's nice. 25 minus 20 is 5. So we say, okay, 5 plus 6z equals negative 7. I can subtract 5. 6z is negative 12. Or divide. Here we can do it without having an intermediate step. Negative 12 divided by 6 is negative 2. So the other point is minus 3, 5, minus 2. And we're done. So it turns out there are 2 points. So all the points are 2 points, where when we look at our tangent plane to our surface at our point P, that we can use the normal vector as 3, 2, 2. Good times, good times. Use a directional derivative to approximate the amount by which the function f of xyz equals 2x minus x sine z plus 3y cosine z plus 4z changes when moving from the point p0, 1, 2, 0, a distance of ds equals 0.3 units towards the point 7 minus 1, 2. What? What? What does this ask us to do? Okay, so this sounds complicated, so let's step back. So we have a function of 3 variables. So this is kind of hard to visualize because it's not like, oh, yeah, when a function of 2 variables, the third thing is like elevation. It's like, oh, it's a surface up here. Function of 3 variables, I oftentimes think of it as like visualization of like density, or there's like a measurement going on in a 3-dimensional space. And so, okay, so what's happening is, let's suppose, let me see, do I have a dark color? This is a darkish color. All right, so I'm in my 3-dimensional space, and we're at a point. So here's our point. We'll call this P0. It's not actually where P0 is, but let's pretend like it was. And here's a point P1. Now, what's happening is we want to approximate the amount by which the function changes. Now, there's a couple of lovely words here. It's an approximation, that's good. And when we think approximation, we think of like tangent planes. We'll get into that in just a second here, what that means. But we're moving in this direction. So it's like, okay, so we're moving this way. But how much are we moving? Well, we're only going to move a set amount. So I'm going to only move a distance of 0.3 along the direction from here to there. And I say, okay, that's how far I want to move. And now the question is, what is going on at this point? But more particularly, how much have I changed? So what's the change? All right. So how do we find this? Well, we can think of this in a couple of different ways, but really, you say, look, this tells us how far we're moving. So what do we need? We need a rate of change. So we say, oh, that's like a rate of change in a particular direction. Are you asking for a directional derivative? Yes, we are asking for a directional derivative. So what we want is a directional derivative. And then we say, okay, that tells us our rate of change. This tells us how much we want to change our inputs. So we're going to take our directional derivative and multiply it by 0.3, and that'll be our estimate. Doesn't sound so bad. So let's see if it actually, what the computations are going to be. Okay, so we have a plan. Let's just make a plan. All right. Find our, step 1, find our directional derivative. All right. Step 2, multiply by 0.3. Step 3, not so sure on, but then, yes, this is always my favorite plan. Okay, so there's our plan. All right, so we're going to begin. All right, well, how do we find directional derivatives? We say our directional derivative in the direction of u for a function f at a point P is the gradient of that function at P dot u. So let's talk about our gradient. Our gradient of f will be, and take derivative with respect to x. We have 2 minus sine z, and then, let's see, any other x's? No, that's it, comma, 3 cosine z, and that's the only y, okay, comma, and okay, here's something, there's a minus x cosine z, and let's see, oh, here's another one, minus 3y sine of z, and a plus 4. Okay, all right, so there's the gradient of the function. So we took all the partial derivatives. Now we're plugging in our point 1, 2, 0. So everywhere we see an x, put a 1. Where you see a y, put a 2. Where you see a z, put a 0. Okay, so 2 minus sine of 0. Sine of 0 is 0, comma. 3 times cosine of 0. Cosine of 0 is 1, so that leaves us with 3. Then we have minus x minus 1 times cosine 0, minus 1. 3 times 2 times sine of 0, 0. And then plus 4 is, well, plus 4. So that gives us the vector 2, comma, 3, comma, 3. Okay, so that's the gradient of f. Now, what's u? Well, okay, we know we're going from P0 to P1. So we'll start with the vector that goes from P0 to P1. So what is that vector? P0 to P1. Well, we say, what's the change? I went from 1 to 7. That went up by a positive 6. 2 to negative 1. That went down by 3, so negative 3. 0 to 2, that's a positive 2. Now, that vector is not a unit vector. The entries are way too big. Too big. Too big. Gotta make them small. So, we're going to figure out how big is this vector. We're going to find its length. So the vector P0, P1 has length square root 36 plus 9 plus 4. So we're just, a squared, b squared, c squared. Square root of 49, that's 7. So our unit vector is 1/7 times the vector 6 minus 3, 2. All right, good. Now, we're almost there. We're almost there. So, we found our gradient of f. We found our u. So we're going to put them together. And we say, okay, our directional derivative, our du fp, is 2, 3, 3 dot 1/7 6 minus 3, 2. So the 1/7 you can just pull that out in front. 2 times 6 is 12. 3 times negative 3, subtract 9. 3 times 2, add 6. Well, 8, let's see, 12 minus 9 is 3, and 3 plus 6 is 9. All right, so we get 9. So we get 9/7. Perfectly fine answer, 9/7. All right, good, good. We're on track. We've done step 1. Now, recap. Why did we do step 1? we're looking for an estimate of change. When we're estimating change, you say, what's my rate of change and how much have I moved? The rate of change is a derivative. And because we're talking about moving from one point to another point, that's rate of change is coming from a directional derivative. Okay, so that's why we did step one. Now if I want to estimate the change, I say, okay, I know my rate of change. How much have we moved? That's this quantity. That's that distance. So our answer is, we can say, look, now our, let's be careful. Use the directional derivative to approximate the amount by which the function changes. Okay, our change is approximately 9/7 times 0.3. I'll write that as 3 over 10. And if we do that, we end up with 27 over 70. We don't have anything else to describe, change, because we don't know what the measurements for f are. So we'll just say 27 over 70. There's the estimate for our change. All right. Then what happens? Well, we're out of time for this problem. So we'll never find out that beautiful missing step. Maybe the next one. Find and classify the 3 critical points of this function. 3x squared y minus 2x cubed plus 3y squared minus 24y plus 11. Well, I hope we find 3 critical points, because if we don't, that's not good. Okay, so whenever we have find and classify, always 2 steps. We always have step 1, find, always step 2, classify. So we start with the find. Well, to find, that's where we have a flat tangent plane. Think of it back, channel your inner Calc 1, that innocent, sweet child. We were so young back then. And we said, critical points, that's where like the derivative is 0. For us, that's where the gradient is 0, which means partial derivatives are 0. All right. So we're going to set 0 equal to our partial derivatives. G sub x equals, all right, here we go, 6xy minus 6x squared, and nothing, nothing, nothing. Okay, then 0 equals g sub y. Okay, well, there's a 3x squared, and that goes away, plus a 6y, and a minus 24. All right, now, let's pause for a second and ask, what do we do in these types of problems? Well, what you're looking for is a way to solve. And when you have x's and y's being mixed together, there's lots of ways you could approach it, but our mindset is, let's try to keep things simple. So the first thing you should always look for is, does anything factor? Because if it does, life is good. So we look at this. We really look at it and say, is it going to factor? Well, the first one, that's got a good shot, doesn't it? If we look at it and say, well, hey, both terms have 6 and both have x. So this gives us 6x times y minus x. And we're like, whoa, factored. Now, why do we like factoring? Well, because it turns it into sort of small collections of problems. And we say, we now sort of have 2 branches. It's like we have a choose-your-own-adventure, but with math. So what do I mean? Well, we have 6 times x times y minus x equals 0. So either the x part equals 0, or the y minus x part equals 0. Okay, good. So that leads us down to 2 roads. 2 roads diverged in a mathematical woods, and happy we get to travel both. So now let's do our cases. So let's start with x equals 0. So the punchline is, as long as x equals 0 or y minus x equals 0, the first equation is true. And if neither of those is true, the first equation doesn't hold. So one of those has to be true. So say, okay, well, suppose x equals 0. Now we know the first equation is good to go. So what does it say about the second equation? Well, since x equals 0, that goes away. It tells us that 6y minus 24 equals 0, or 6y equals 24, or y equals 4, which gives us 1 point, namely x equals 0, y equals 4. 0, comma, 4. All right, 1 point down. We'll put a little squiggly line just to help us remind ourselves that that's there. Now, y minus x equals 0, we could also describe this as the y equals x. Okay, so go to our second equation. Well, since y equals x, we can replace y by x or x by y. So this says, hey, this can become 3x squared plus 6x minus 24 equals 0. Now everything has a 3, so let's go ahead and divide out. X squared plus 2x minus 8 equals 0. Now, does it factor? Have our instructors been nice to us? I hope they have, because they seem like such nice people. They're the kind of people who you'd be like, hey, and then they'd be like, hey, and we'd like, yeah, lots of love that goes on in the math department. Okay, so you need two numbers that multiply to -8, add to +2. Can you do it? Yeah. You could do x plus 4, x minus 2, right? X squared, good. Minus 2x plus 4x plus 2x and minus 8. So, again, we get kind of a splitting here. You get x is either -4 or x is +2. Now, if x is -4 and y equals x, that gives the point -4 comma -4. So there's a second point. Aha, cool. Or if x equals 2 and y equals x, well, that gives the point 2 comma 2. A third point. We said we needed 3, and we got 3. Woo! Look at us getting 3 critical points. Yeah, we're doing great. And we still have plenty of space left to do the second part. All right, so let's celebrate by checking off we've done our find. We have found our critical points. Nice. Nice. All right, well, catching our breath, we transition off to the classifying. So, second partials test. All right, so let's recap second partials test. So we're going to find this D, which is gxx, gyy. We're going to subtract gxy quantity squared. And there's a couple cases. If D is positive, we then say, well, look at gxx. If that's negative, then we are a max. If gxx is positive, we are a min. If D is negative, we are a saddle. And if D equals 0, we draw no conclusions. It's a judgment-free zone. So if your discriminant is 0, we make no judgments. We say, we just don't know. The test is inconclusive, and that's that. All right. So we need to find our second derivatives. Good news, we've already found our first derivative, so that shouldn't take us too long. Gxx is, well, derivative of 6xy with respect to x is 6y. Derivative of 6x squared is minus 12x. Gxy, derivative with respect to y, first term will give us 6x, the second term goes away. We could also have done g sub y, take the derivative of that with respect to x, we'd have gone 6x, because they're going to match, especially in these kinds of problems. Gyy, well, okay, derivative of g sub y with respect to y, that goes away. That's going to be 6, and that goes away. All right, good news. we are definitely not going to have a max. Now you might say, wait, what? How can you tell already? Look at GYY. What do you notice? It's positive. That says you can't be a max, because this test for GXX is also the same as if you plug in GYY. Okay, so we either have a min or a saddle or a... Okay, so putting this together, we get that our function d is 6y minus 12x, and then we also have times 6 subtract 6x squared. Okay, and now we have to plug in our points. Okay, so let's start. We're going to plug in 0, 4. D of 0, comma 4. Well, 6 times 4 is 24, subtract 0. So that's 24. 6 is 6. 6 times 0 is 0. And we're going to square it. Now, do we need to know that this is 144? No, we do not need to know that's 144. What do we need to know? We can know that it's a positive number. So, it's positive. So we're like, nice! So then we say, okay, now go into your second partials, which really is looking at the slices. Say, okay, this is a positive number. We're at a min. So this point 0, 4 is a minimum. Okay, great. Nice. Well, we still have other points. Okay, so let's plug in, say, negative 4, negative 4. Well, that'll be minus 24 plus 48. Minus 24 plus 48, that's positive 24 again, times 6. Then we're going to subtract minus 24 squared. Now, do we need to know that 24 squared is 576? We do not. Does it help us? Yeah, kind of. What do we care about? What's the sign? 24 times 6, subtract 24 squared. Which one's bigger? The 24 squared is definitely bigger. So what's that going to tell us? It tells us it's negative. So that tells us that this point is a saddle point. All right. Good. Now, one more point. Where's our last point? 2, 2. All right, 2, 2. Ballerinas dancing through our heads. 12 minus 24 is negative 12, right? 12 subtract 24. Yeah, that's definitely a negative number. Times 6 subtract 12 squared. Well, it's negative 72. Subtract 144, so it's a negative and another negative, very negative. So negative tells us it's a saddle. Now, I will say there's lots of saddle points, and it tends to be the case that almost always, if you have multiple points, usually most of them will be a saddle point, and then one will be a min and one will be a max. There are a few occasions when we've been just clever enough as problem writers to get both a min and a max, but we tend to have lots of saddles. I just want to be honest with you. Don't be surprised if you keep seeing like, why do I keep getting so many saddles? It's not you, it's just math. It's just the way it is. But all right. Yay! Woo! What a workout. We should have celebrated. We forgot to put the mark here because we have found and classified, and we have 3 points, and life is good. Woohoo! Nice. Suppose that g of xy is a function having second-order Taylor polynomial. P of xy is this expression at negative 1, 1. Find the linear approximation to g of xy at negative 1, 1. Now you might say, oh, well, that's easy. I just have to do the part that looks like a plane, right? It's there, right? 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 No, because whoever wrote down this second order Taylor polynomial did something quite silly. And it was really a test to see if we were paying attention. What was their silliness? They expanded. See, normally when you have something at x equals minus 1, y equals 1, you'd have like x plus 1, y minus 1. And we don't have those. So what they have done is they have expanded and then grouped the coefficients together. Why did they do that? Probably because they just remember their algebra teacher saying, keep expanding, practice your expanding. And so they're like, okay, I'm going to expand. So how are we going to recover it then? Well, the good news is it's actually pretty straightforward. We say, aha, insight. You see, this function is storing derivatives, because that's what Taylor polynomials do. They store derivatives. And in particular, we say this is going to match the function, the first derivatives, and the second derivatives. That's the whole punchline here. Because it's the second order Taylor polynomials, it has to match. That's how you make this. Okay, so given that that's true, how do we exploit this? Well, we say, well, we're just going to see what is the value of this function. What is the value of this function's derivatives? And then we're going to use those. And like, okay, well, let's do that. So we have our p of xy, and I'm just going to copy it down again. 4 minus 2x plus 5y plus x squared minus 3xy plus 2y squared. And I'm going to look at the partial derivative. So p sub x of xy. Take derivative with respect to x. Negative 2 plus 2x minus 3y. Take derivative with respect to y. P sub y of xy. 0, 0, 5. 0 here, we'll get minus 3x. And here we'll have plus 4y. Now, so we've taken the function and the first order derivatives of p. What happens when we plug in minus 1, 1 has to agree with what the function would do at minus 1, 1. So our great insight is that g at minus 1, 1 has to match p at minus 1, 1. And so let's plug in. So that's going to be 4. X is a minus 1, so plus 2. Y is a plus 1, so plus 5. Minus 1 squared makes plus 1. Minus 3 times minus 1 times 1 makes plus 3. Plus 1 squared is plus 2. So we have 4 plus 2 plus 5 plus 1 plus 3 plus 2. Well, there were so many things I lost track. So, but 2 plus 3 is 5. There's a 10. And then the rest it makes up 7. So that makes a grand total of 17. Okay, so the function at minus 1, 1 is 17, not 4. All right. Same ideas. G sub x at minus 1, 1 has to match p sub x at minus 1, 1, which is negative 2. X is minus 1, so negative 2. And y is 1, so minus 3. Minus 2 minus 2 minus 3, negative 7. And g sub y at minus 1, 1 has to equal p sub y at minus 1, 1. So that's 5. Minus 3 times minus 1 makes plus 3. And then 4 times 1 makes 4. 5 plus 3 plus 4 is positive 12. So our linear approximation, g of xy, well, the generic formula for it would be g at minus 1, 1 plus g sub x at minus 1, 1 times x minus minus 1 plus g sub y at minus 1, 1 times y minus 1. but we know these numbers. So we have 17 minus 7 times x plus 1 plus 12 times y minus 1. And we're not going to expand because we don't need to. We found our tangent plane, our linear approximation, our first order Taylor polynomial, all those lovely terms, all true things. And there we go. We undid their mistake in some sense, or at least partially undid it. All right. Woo! Yay! We did it! We did it! High five! Oh, slow down there, Tiger. All right. Thanks for joining. Hope you had a great time. Hope you're doing well. I hope this is making sense. Taylor polynomials, sometimes people feel like, it's like flashbacks to calculus, like, but they're not so bad. You can do this. The second time through, you're like, oh, you're just doing better approximations. I like approximations. I'm an engineer, or maybe you're not an engineer, but you're still like, I like approximations. Okay, I should stop rambling before I get myself into too much trouble. See you again.